Hello everyone, I am Brian Macon. Welcome back to the Math Fun Room. In this video, we're going to begin learning about parabolas. Parabolas have a really interesting reflective property that can be observed in lots of different applications, like satellite dishes. Before we get into those applications, we're going to want to begin by defining the parabola algebraically and identifying some of its properties. So let's get started. Let's begin by considering the definition of a parabola. A parabola is the collection of all points P in a plane that are the same distance d from a fixed point F as they are from a fixed line D. The point F is called the focus of the parabola, and the line D is its directrix. As a result, a parabola is the set of points for which the distance from F to P is equal to the distance from P to D. The given figure on this slide shows a parabola in blue. The line through the focus F and perpendicular to the directrix D is the axis of symmetry of the parabola. The point of intersection of the parabola with its axis of symmetry is the vertex V. Because the vertex lies on the parabola, it must satisfy the definition. In other words, the distance from the focus to the vertex must equal the distance from the vertex to the directrix. The vertex is midway between the focus and directrix. Therefore, the vertex is midway between the focus and directrix. We let the number a represent the distance from the focus to the vertex, where a is positive. In order to derive the algebraic equation of a parabola, we will conveniently locate the parabola in a rectangular coordinate system. On this slide, we have four graphs of a parabola. Figures A and B place the vertex at the origin, and the parabola either opens to the right, as shown in figure A, or to the left, as shown in figure B. Note that the focus is on the side of the vertex in which the parabola opens, and thus the parabola opens away from the directrix. In figure A, the focus is on the positive x-axis, and the focus is on the negative x-axis in figure B. Figures C and D place the vertex at the origin, and the parabola either opens up or opens down, respectively. Note that in figure C, the parabola opens up, and the focus is on the positive y-axis. In figure D, the parabola opens down, and the focus is on the negative y-axis. Let's step back for a moment and derive the equation of the parabola with vertex at the origin. First, let's consider the case where the focus is on the positive x-axis. Because the distance from the focus to the vertex is a, then the focus is located at the point a, 0, again with a positive. Similarly, because the distance from the vertex to the directrix is also a, and because the directrix is perpendicular to the axis of symmetry, which is the x-axis in this case, then the equation of the line that is the directrix is the vertical line x equals negative a. Now recall that the definition of a parabola states that the parabola is the collection of all points that are equidistant from the focus and the directrix. So for any point P with coordinates x, y that lies on the parabola, the distance from the focus to P must equal the distance from the directrix to P. Now to calculate the distance from F to P, we can use the distance formula and write square root of the quantity x minus a squared plus the quantity y minus 0 squared. Now the distance must equal the distance from P to D. Now note that the distance from P to D is a horizontal distance, thus the distance is absolute value of the quantity x minus negative a. Now with the equation that relates the two distances being equal to each other, let's square both sides of the equation and write it in an equivalent form. The quantity x minus a squared plus the quantity y minus 0 squared equals the quantity x plus a squared. If we multiply out the binomials that are squared, that is x minus a quantity squared on the left-hand side and x plus a quantity squared on the right-hand side, our equation becomes x squared minus 2ax plus a squared plus y squared equals x squared plus 2ax plus a squared. Subtracting x squared from both sides and subtracting a squared from both sides, we end up with the equation y squared equals 4ax. So this is the equation of the parabola with vertex at the origin and focus at the point a, 0. In summary, we present the following theorem for the equation of a parabola with vertex at the origin. The theorem states the equation of a parabola with vertex at 0, 0, focus at a, 0, directrix at x equals negative a, where a is positive, is y squared equals 4ax. Let's consider an example of finding the equation of a parabola and graphing it. Now this problem states, find an equation of the parabola with vertex at 0, 0, and focus at 2, 0, then graph the equation. Now to begin, we know the general equation of the parabola has the form y squared equals 4ax. Now since the focus is at 2, 0, then we know that the value of a equals 2. Now substituting a equals 2 in the general equation, we get y squared equals 8x. Now at this moment, I'd like to go ahead and plot the information we know up to this moment. So using a rectangular plane with x-axis from -2 to 9 and y-axis from -6 to 6, let's plot the vertex at the origin, focus at the point 2, 0, and the directrix at x equals -2. Now keep in mind the line that is the directrix does not contain any points that lie on the parabola, so we typically sketch the directrix using a dashed or dotted line. We know that the parabola could be sketched at this point by having it open to the right from the vertex, with the x-axis being the line of symmetry. However, we want to be a little more detailed and make sure we give the parabola the proper width to the opening. Now to accomplish this, we will plot a few points on the parabola, and in particular, we will use what is called the latus rectum, which is the line segment joining the 2 points on the parabola at x equals a, or in this case at x equals 2. Now substituting x equals 2 into the equation y squared equals 8x, we get y squared equals 16. And solving for y, we find that y is equal to plus or minus 4. So let's plot the points 2, 4 and 2, -4. Now for our initial conversation, I'm going to use a line segment to connect these 2 points we just plotted, which represent the endpoints of the latus rectum. However, in the future, we only plot the 2 points, and we will not actually sketch a line segment when drawing the parabolas. So now that we have plotted all of the guiding information, let's draw the parabola from the vertex through the point 2, 4, and from the vertex through the point 2, -4. One final note, if we wanted to graph the parabola y squared equals 8x on a graphing calculator, notice the parabola is not a function. It fails the vertical line test. So we would have to actually graph the upper branch of the parabola and the lower branch of the parabola in function mode on our calculator. Now, if we solve the equation y squared equals 8x for y, we would have to plug in the 2 equations. Y1 is equal to square root of the quantity 8x, and y2 equals negative square root of the quantity 8x. In this example, we're told to analyze the equation y squared equals 12x. For the remainder of our conversation, the direction to, quote, analyze the equation, unquote, means to find the vertex, focus, and directrix of the parabola and then graph it. So to begin with this problem, we know the general equation of the parabola has the form y squared equals 4ax. Therefore, it must be true that 4a equals 12, which means that a is equal to 3. So then, the focus will be the point 3, 0, and the directrix the line x equals -3. Now let's plot the information we know up to this point. So using a rectangular plane with x-axis from -4 to 8 and y-axis from -6 to 6, let's plot the vertex at the origin, the focus at the point 3, 0, and the directrix being the vertical line x equals -3. Now let's determine the endpoints of the latus rectum by substituting x equals 3 into the equation y squared equals 12x. So this gives us y squared equals 36. And solving for y, we find that y equals plus or minus 6. So let's plot the 2 points 3, 6 and the point 3, negative 6. Again, these 2 endpoints represent the endpoints of the latus rectum. We're not going to actually sketch that line segment because these 2 points lie on the parabola. So now that we've plotted all of the guiding information, let's draw the parabola from the vertex through the point 3, 6 and from the vertex through the point 3, negative 6. Recall that we obtained the equation of the parabola after placing the focus on the positive x-axis. We could place the focus on the negative x-axis, the positive y-axis, or the negative y-axis, which would result in slightly different forms of the equation. Now, the 4 forms of the equation of the parabola with vertex at the origin and focus on a coordinate axis that is a distance a from the vertex, a being positive, are given in the following table. So let's take a moment to read these 4 descriptions and equations. Now keep in mind, all of these parabolas have a vertex at the origin. So the first equation is the equation we've already considered, which is the equation y squared equals 4ax. The focus was on the positive x-axis at the point a, 0, and the directrix was the vertical line x equals negative a. Now the description is that the axis of symmetry is the x-axis and the parabola opens to the right. The second equation would be y squared equals negative 4ax. This would have a focus on the negative x-axis at the point negative a, 0, and directrix being the vertical line x equals a. Now this parabola also has an axis of symmetry that is the x-axis, but the parabola opens to the left. The third equation is x squared equals 4ay. Now this focus lies on the positive y-axis at the point 0, a, and the directrix is the horizontal line y equals negative a. Now this parabola has an axis of symmetry that is the y-axis, and the parabola opens up. The last equation is x squared equals negative 4ay. The focus is on the negative y-axis at the point 0, negative a, and the directrix is the horizontal line y equals a. Again, this parabola has an axis of symmetry that is the y-axis, but the parabola opens down. In this example, we're told to analyze the equation x squared equals negative 8y. Now to begin, we know the general equation of the parabola has the form x squared equals negative 4ay. Therefore, it must be true that 4a is equal to 8, which means a is equal to 2. So then, the focus will be at the point 0, negative 2, and the directrix the line y equals 2. Now let's plot this information we know up to this moment using a rectangular plane with x-axis from negative 6 to 6 and y-axis from negative 6 to 6. Let's plot the vertex at the origin, the focus at the point 0, negative 2, and the directrix the line y equals 2. Now let's determine the endpoints of the latus rectum by substituting y equals negative 2 into the equation x squared equals negative 8y. Now this gives us x squared equals 16, and solving for x, we get x is equal to plus or minus 4. So let's plot the points 4, negative 2, and the point negative 4, negative 2. Now that we've plotted all the guiding information, let's draw the parabola from the vertex through the point 4, negative 2, and from the vertex through the point negative 4, negative 2. In this example, we're told to find the equation of the parabola with focus at the point 0, 3 halves, and directrix the line y equals negative 3 halves. So to begin, let's plot the information given on the xy grid to start visualizing the graph. Using a rectangular plane with x-axis from negative 5 to 5 and y-axis from negative 5 to 5, let's plot the focus at the point 0, 3 halves. Next, plot a horizontal dashed line at y equals negative 3 halves to represent the directrix. Now, since the vertex lies midway between the focus and directrix, then we plot the vertex at the origin. Since the focus is on the positive y-axis, then the equation has the form x squared equals 4ay with a equal to 3/2. Substituting in the value of a, we get the equation x squared equals 4 times 3/2 times y, which equals 6y. So we've accomplished the first part of this problem, which is finding the equation of the parabola to be x squared equals 6y. Now that we have the equation, let's finish graphing the parabola. So to do this, we will find the two endpoints of the lattice rectum by substituting y equals 3/2 into the equation x squared equals 6y. This will give us x squared equals 6 times 3/2, which is 9, and therefore x is equal to plus or minus 3. So on our xy grid, let's plot these 2 points at 3, 3/2 and -3, 3/2. Now that we've plotted all the guiding information, let's draw the parabola from the vertex through each of the 2 endpoints of the lattice rectum. In this example, we're told to find the equation of the parabola with vertex at 0, 0, if its axis of symmetry is the x-axis, and its graph contains the point -3, 2. Find its focus and directrix and graph the equation. So to begin, let's plot the information given on the xy grid to start visualizing the graph. Using a rectangular plane with x-axis from -5 to 5 and y-axis from -5 to 5, let's plot the vertex at the origin as well as the point -3, 2. So since the axis of symmetry is the x-axis, then we know the parabola will open to the left from the vertex passing through the given point -3, 2. So I'm going to draw the upper half of the parabola passing through the vertex and the given point. Therefore, we know the general equation of the parabola would have to be y squared equals -4ax. Now, because the point -3, 2 is on the graph of the parabola, the coordinates must satisfy the equation. So let's substitute x equals -3 and y equals 2 in the general equation and write 2 squared equals -4 times a times -3. And solving for a, we get that 4 is equal to 12a, or 1/3 equals a. Now, substituting the value of a back into the general equation, y squared equals -4ax, we get the equation y squared equals -4/3 times x. And thus we have determined the equation of the parabola. So now we can determine that the focus is the point -1/3, 0, and let's plot that point in the xy plane. And in addition, we know that the directrix will be the vertical line x equals 1/3, and let's plot that dotted line in the xy plane. Now finally, due to the symmetry to the x-axis, we can plot the point -3, -2 and sketch the bottom half of the parabola passing through this point and the vertex at the origin.